Hello, I'm back here to continue your blood discussion. Blood. I don't know if you saw the little video, thought it was humorous. We left off last time looking at the red blood cells, right? Hematocrit, red blood cells, the maturation process of how those cells become functional, right? So I'm going to continue on today with the same slideshow. But we look now at the white blood cells, so the buffy coat. So normally we extract blood, we do the centrifugation, we generate a hematocrit. We're looking at that little tiny buffy coat here, right? So 45% of the red blood cells, 55% of the plasma. Now we just have that little tiny bit in circulation that are the leukocytes, white blood cells. So literal translation, leuko referring to white, cyte referring to cell. So literal translation, white cell. Normal everyday vocabulary, we say, well, they're white cells, but they're blood cells. So we call them white blood cells. So collectively, these cells are going to protect the body against disease. They're gonna help in the immune response, keep the body safe, keep the body healthy, right? Against foreign invaders, against self aspects, such as cancers and different things like that. So I'll give you some more specifics in a bit. So a big distinction between red blood cells and white blood cells, these leukocytes are actually complete cells. So they do retain their nucleus. They maintain their mitochondria, all their organelles. So they're long-lived, functional whole cells. Yeah. The way that they're going to be sort of analyzed and identified, and if we were in lab, we would do some of these techniques. I'm going to have to find a way how to blend in the concepts and the theory into the practicality. So I'll figure something out. But again, we would stain and we would further identify the cells based on their size, based on the shape of their nuclei, whether or not they have granules, what color the granules stain, that kind of stuff. So I'm gonna make sense of all this mess. And the homework does address some of this. So I may just sort of extract a grade from your relevant homework questions that deal with the anatomy, the identification of these leukocytes. We'll see how that progresses. So you've seen this picture before, right? If we had a microscope, a normal human slide, a normal human blood slide in front of us, we would see the normal representation, 55% plasma, 45% erythrocytes, and only a very small number of leukocytes. So they account for less than 1% of blood volume. So very, very minimal. For you range nursing types, there's the normal values. So, and if you notice, they look different, right? They're different colors, different shapes. So those are defining characteristics of these individual leukocytes. So of that less than 1% in circulation, we would then have the ability to distinguish between granulocytes and agranulocytes. So this is a distinctive process that allows us to further differentiate, further identify, further define the actual type of leukocytes. So of our formed elements, right, this is the excluding plasma, 45% erythrocytes, less than 1% of our leukocytes, and a slightly higher amount of platelets. So we'll address those in another lecture. So right now we're focusing only on leukocytes, only on the white blood cells. And actually there's not just one type, there's gonna be 5 distinctive types. So we're gonna break those up into the granulocytes and the agranulocytes. So these cells that contain granules and the cells that do not contain granules. And what are granules again? So granules are going to be a concept from 1306. Basically, granules are lysosomes, one of these cellular organelles that we find in cells, right? In plant cells, or I should say more in animal cells. So granules help with the cleanup process. Granules, lysosomes are going to be involved in the removing of dead tissue, sort of cleaning up the area. So again, important distinction, whether granules are present or they're absent. So that will help make sense of the granulocytes or the agranulocytes, right? So these two very, very distinctive types of cells there, granulocytes, agranulocytes. So granulocytes will include things like what we call neutrophils, eosinophils, and basophils. So neutrophils, eosinophils, basophils, all the phils. And phils, if we look at the Greek language, if something is a hydrophilic, it means it loves water, right? Phil. So this is gonna love neutral stains. These are gonna love different eosin, a different type of stain. That's how the names are derived here. If we have an A out before the name, that means without. So these are the leukocytes without granules. So the agranulocytes. These are going to be the cytes, lymphocytes and monocytes. So again, 5 total categories of lymphocytes, right? Neutrophils, eosinophils, basophils being your granulocytes, lymphocytes and monocytes being under the agranulocytic sort of distinction. And these are not in equal representation either, right? So if you notice, big chunk being neutrophils, smaller chunk, tiny chunk being basophils. So there is a little mnemonic that's sometimes used. Maybe you can think of your own, but the way I learned it when I took, when I learned this stuff, it was never let monkeys eat bananas. I don't know, I guess they like bananas, but you should never let monkeys eat bananas, right? So never, neutrophil, let, lymphocytes, monkeys, monocytes, eat eosinophils, and bananas, basophils. So it's a way of remembering the most abundant to the least abundant amount of white blood cells, right? So never let monkeys eat bananas. And if we notice neutrophils, the greatest abundance at 50 to 70%, lymphocytes 25 to 45, eosinophils 2 to 4, monocytes 3 to 8, and or I should say, never let monkeys, monocytes 3 to 8, eat eosinophils 2 to 4, and then bananas 0.5 to 1%. So just may help you with the homework there. All right, so something that you should remember from last discussion are hemocytoblasts, right? That pluripotent cell, that precursor to all the blood cells, that stem cell, if we want to kind of call it like that. So very early in its development, very early in its progression, we see a distinction here. And if we go to the lymphoid stem cell or the myeloid stem cell, that will then determine the line, the lineage of leukocyte that we're going to have, right? So if we go this path, if you notice, nucleus stays intact, and we end up with the lymphocyte. If we go down this path, we can go now through 4 different pathways to generate the eosinophils, the basophils, the neutrophils, and the monocytes. So there's a little bit more complexity here in the development of a white blood cell than there is for the development of a red blood cell. So these developmental pathways. Now, I'm not going to get that particular in the different names. There's a lot of names to remember, right? The band cell, the myelocyte. There's a lot of little names. I just want you to kind of get the big picture. We need this to generate this, and then we need this cell the myeloid stem cell to generate these 4 of the monocytes. Very different line being the lymphoid cells over here. Lymphocytes are their own, they're kind of rebellious. They're different, and they're going to have a different anatomy. They're going to have a different physiology as well. So let's start off with our granulocytes, right? The lysosome containing leukocytes. So the neutrophils, so have granules or lysosomes, which are going to be involved in releasing different defensins and different peroxide bursts, oxygen bursts, that kind of stuff to kill foreign particles. Yeah. So neutrophils, I like to think of them as our first responders. If we were to call 911, the first sort of people to arrive, that would be the analogous situation of a neutrophil. There's a cut, there's an infection, there's some call for help. Well, who shows up first? That's going to be our neutrophils. Right? So first, white blood cells to show up at the infection site. They will increase in numbers during acute infections, acute being important here. They are basically our bacteria specialists. So they are very, very good at detecting, at removing, at destroying bacteria. So obviously there's a lot of bacteria around, so makes sense. A lot of bacteria. We have very high numbers of neutrophils, and they're first to the scene there, right? So they also can help out with fungi. They're not specialists with fungi, but they can help. And they're going to be involved in these antigen-antibody complexes that we're going to get into later in the immunology chapter. So neutrophils, these granulocytic cells, are going to be considered to be polymorphonuclear, PMNs, right? Polymorphonuclear. And what that means is the nucleus isn't just round like what you learned in 1306. In this situation, the nucleus has these little lobes, these different shapes, right? That's one nucleus, this dark purple structure. That's the nucleus within the leukocyte there, right? So we have one lobe, we have this weird lobe. So all this mess here being our polymorphonuclear shape. So neutrophils are going to have between 3 to 6 nuclear lobes. So we can say there's one lobe, maybe 2, maybe 3, maybe 4, right? Depending on how you want to analyze that. But that's completely normal for these cells, and it doesn't affect the way that they function. Why they're like that, I honestly am not quite sure. But I do know that it helps the cell find and remove bacteria in the body. So neutrophils don't typically live in circulation, just like firefighters or ambulance riders don't live driving on the streets, right? They hang out at their stations. When they're called, they rush to the highways and they can be seen in the streets, but they don't live on the streets, right? They live in their own little stations. That's kind of how neutrophils are. They don't spend a whole lot of time in circulation, maybe 10 to 12 hours. And then once they find where they need to go, they leave circulation and enter into the tissues where they can survive for a little while, 1 to 2 days. They're sort of like warriors. So they have the ability to repair themselves, but many times they get lost in battle, right? They get damaged beyond the point of repair. So again, kind of a short lifespan. They can live long. When they're called for action, then they basically have a short lifespan that they can function there. So the neutrophils, polymorphonuclear cells. Next, we'll have the eosinophils. So eosinophils are parasite specialists. These eosinophils are parasitic worm type of specialists. And let's say we are talking about a puppy, right? You got a new puppy. We know that we have to give the puppy shots, and probably we have to deworm that puppy. Humans, I should say most mammals, have co-evolved with parasitic worms. These worms that get in our intestinal tract and in our body, roundworms, tapeworms, these kind of things. So, well, it's not a big deal in the immune sense. So our body has dealt with parasitic worms for a long time, and we have developed a defense mechanism for these parasitic worms, and those are our eosinophils, right? So eosin, it doesn't necessarily describe what the cell is. Eosin is a red stain, so it basically stains these cells red, and that's where they get the name. So red stain loving cells, eosinophils. These are the parasitic specialists here. Eosinophils' primary roles, parasitic diseases, but they can also have an impact on allergies, right? They're gonna not allow allergies to flare up. So eosinophils kind of keep allergic reactions in check. So we would say a person that has infections, you can say these parasitic worms in their long-term, it has a potential to generate a lot of inflammation, but luckily these eosinophils will target the parasite and try to keep that inflammatory response low. So that's important. It's going to make you feel better, right? It's going to make you not have all the allergic reactions, the inflammation, and trying to get rid of that infection there. So these are also polymorphonuclear, but only with a bilobe nucleus. So again, a pretty distinctive, and I'll show you a picture next here. Right? And then that red stain will stain the granules red. So eosinophils, quite distinctive from the neutrophils. So neutrophils, blue, 3 to 6 lobes on the nucleus. Eosinophils are going to be red. And I don't know about you, but I always, when I see eosinophils, if they're positioned in the right way, they remind me of like little alien heads with sunglasses. There's the alien big eyes or little face with a big red sunglasses. So those are the bilobed eosinophilic structure here. And the red granules, all these little red specks, all the red specks in there, those are the granules of the eosinophils, our parasitic specialists. All right, basophils. So basophils are going to be kind of the opposite of eosinophils. Eosinophils try to dampen, control the immune response, or I should say the allergic response, inflammatory response. Basophils are going to sort of enhance, exaggerate the inflammatory response. So how do they do this? Basophils send this alarm sort of molecule, this vasodilator that we call heparin and histamine. I don't know if you have allergies. If you suffer from allergies, you know, you take Claritin, you take Benadryl to sort of have the antihistamine response. Well, basophils roll, they're very small. Physically, they're very tiny. And they're like little tattletales, basically. If you have a little brother, little sister that you grew up with, if you did something wrong, ooh, the little tattletale is going to run and tell mom and tell dad and get you in trouble, right? They're going to sort of attract attention. Oh, he broke this. Oh, he did this, right? So basically, that's the role of basophils. They produce histamine, which triggers a whole set of immune reactions, and we'll talk about those later. Histamine released by the basophils is involved in both allergic and inflammatory responses. So we do want, if something bad is happening, we do want to call 911, right? We want help to arrive. But let's say help arrives, basophils continue screaming for help, even when help is present, right? So by doing so, they elongate, they extend the inflammatory and the allergic process. That can be, again, not a good situation in that reaction there. So basophils, they're big cells. I should say that they have that large distinctive nucleus, sort of polymorphonuclear again, blue. That's pretty typical, dark purple to blue. So visually, we would be able to see them pretty distinctly there, right? And again, the bananas, right? They're the least common, and that's good, because imagine that these were the most abundant. That would mean that we have a very long, drawn-out inflammatory response. That's not the case. Basophils are the least abundant of these white blood cells. So again, those three make up our granulocytes. So backing up here. So here, kind of in a picture, we see our red eosinophil, little sunglasses, alien eyes, the dark blue to purple basophils, and then the sort of polymorphonuclear, multinucleated neutrophils. So those three collectively make up our granulocytic leukocytes. We go forward over here to the agranulocytes. So agranulocytes are going to look a lot cleaner, right? So down here we have our granulocytes, little specks, all those lysosomes, those granules that are absent in the agranulocytes. We have two, right? We have the lymphocytes and the monocytes here. So big monocytes, small lymphocytes. Lymphocytes are the smallest physically, the physical, size, smallest of the white blood cells. They have a big nucleus though, right? I always thought this was kind of weird. They have, imagine that little small wimpy person, but with a huge brain, right? So they're very small. They don't have much cytoplasm. Their whole cell is basically a nucleus, right? There's not a lot of other stuff in there. So it's not a lot of other space for cytoplasm, for organelles. It's just this really big brain that they have. Right? So these also, we don't find them very much in circulation. They hang out in lymphatic organs. And why do we call them lymphatic organs? Because they are inhabited by lymphocytes, right? So the lymphatic system, lymphatic organs, lymph nodes, spleen, tonsils, inhabited by the lymphocytes, these little agranulocytic little leukocytes there. Lymphocytes are the Einsteins of the white blood cells, the thinkers, the sort of complex behavior, thought process, strategy. That's what we get from the lymphocytes. The granulocytes, basophils, eosinophils, neutrophils, those are like warriors. They go into battle. They're like soldiers. Lymphocytes are going to go into battle, but in a very, very different way, right? They're going to go into battle by producing antibodies. So it kind of reminds me like of a central ground control, right? The big general doesn't go into battle. The big general sends out certain orders and certain, different strategies, long-range missiles, that kind of stuff to attack the enemy. And those long-range missiles are going to be the antibodies. So a big category of lymphocytes. We're going to talk later in the immune system about the B lymphocytes. And then we have the T lymphocytes, which are going to be the warriors that are going to not attack foreign bodies, but that are going to attack irregular self sort of antigens, cells that belong to ourselves, like cancers, right? So a lot of viruses will get into our cells and steal our cellular markers, so they're difficult to detect, and that's going to be the role of these lymphocytes. Lymphocytes have to be smart to distinguish that's a normal healthy cell. This is one of our cells, but infected by a virus. So it has to be very smart to attack the right enemy and not destroy healthy cells. So pretty intelligent category of leukocytes, these lymphocytes. And then we get kind of a big, bulky, U-shaped, very big U-shaped type of nucleus with our monocytes. So monocytes are these big, bulky, bully type cells. Monocytes are going to be very critical in chronic infections. So these long-term infections that go on for a long time. The first responders arrive, neutrophils do what they can, and then they kind of get damaged or go back into tissue. Monocytes are going to stick around for a while, right? These monocytes. Now, there's two terms here, monocytes and macrophages. They are the same thing, basically, yeah? So if I can backtrack here. So you notice we form a monocyte, right? So a monocyte is basically, how do I want to say this? It's like a, maybe you've been certified to do CPR, right? So you have your little card, right? You are certified. But just because you undergo certification, you practice on a dummy, that doesn't mean that you're going to be effective in a real life situation where your skills are required. Right? So this is kind of the certified, but not really having the experience yet. Once it gains experience, once it's modified, once it becomes a very, very good part of our defense mechanism, it transforms itself into the macrophage down below. So the monocyte, with training, with, as they say, man, war changes a person, right? So battle changes a person. Well, battle changes the monocyte into the macrophage. They become very, very much better. They become much improved at helping out with the immune response. So monocytes developing into macrophages. So they're basically one and the same. So it's basically a monocyte on steroids, right? These macrophages, same thing. So again, the monocytes will help with bacteria. They're not bacterial specialists. They will help with other dead cells, junk that's accumulating there. Again, they remain in circulation for 2-3 days. Once they've got their butt kicks a little bit, they go over there, they transform, they strengthen up, they become much better warriors as macrophages, right? So macrophages function in activating lymphocytes to mount the immune response. So we're gonna get to that again in another chapter. These macrophages will coordinate with these lymphocytes, and they really sort of double team and really become a very effective type of long range defender and a very frontline defender here, the macrophages. So important collaboration amongst these leukocytic cells. All right, so hope all that made sense. I know it's a lot to process. I do wish we had microscopes in front of us and we could be looking at the different cells, and if y'all have questions, I could be addressing them at this point, but I hope it's making sense. So we present always how things work, how they're supposed to work, and then we look at maybe some, as they call, leukocytic disorders, homeostatic imbalances of sorts. So first we have the penias, right? Leukopenia. Right? A penia is a deficiency. In the Greek language, penia means to not have enough of something, right? Poverty. So leukopenia, we're poor, we have a deficiency of leukocytes. So abnormally low white blood cell count. This can happen for a couple of reasons. The easiest reason is if a person is fighting cancer and they are, coping against different diseases. They're having chemotherapy. Well, chemotherapy can destroy these white cell counts. There's not a lot of them to begin with in circulation. But again, they can be developing in the bone marrow and other places, so they get wiped out pretty fast. And again, if that happens, and we say that is the state of leukopenia. Now, the body, if given a chance, the body will sort of replenish these. Certain drugs can also have a negative impact on leukopenia or on leukocytes causing leukopenia. The opposite spectrum, so leukopenia not enough, leukemia is too many, right? So leukemia is actually a type of cancer. So leukemia is when we have too many white cells, white blood cells. And there's different variations. Well, I should say there's like 70 variations of leukemias. We can have the acute type of leukemia, the chronic type of leukemias, and depending on the type of cell, right? This is where it gets big, right? Myelocytic leukemia, monocytic leukemia, lymphocytic leukemia. So let me backtrack again. If you can envision or imagine, any one of these cells has the potential to become cancerous. Right? So if this cell right here becomes cancerous, it will have an impact only on the eosinophils. Right? So it's a cancer of those eosinophils. If, let's say, the monoblast has a cancerous situation, it will affect then the progression of monocytes and macrophages. If, imagine the stem cell, the myeloid stem cell becomes cancerous, then it's going to have a bad impact on all of these types of leukocytes. If the hemocytoplast becomes cancerous, every particular red blood cell and white blood cell will be cancerous. So why so many types of cancers? Because it depends on which of these cells in the developmental process is affected there, right? None of them are a good situation. It's still a little bit sad, actually. I don't know if you are aware of our instructor at EPCC, Dr. Dominic Lanuti. He actually was fighting leukemia, right? He was winning the battle, actually. But because of the situation, he went in for chemotherapy. His white blood cell count was too low. His body was not able to mount a good defense. He was, or he contracted the COVID virus in the hospital there, and it just overwhelmed his body. So again, still very close to home. Rest in peace, Nick. But basically, again, this is what did him in. Had he not had leukemia and he picked up the virus, I suspect he would have been able to fight it off. Had he just had leukemia and not the virus, I suspect the chemo would have done what it was supposed to, and he would still be with us today. It's just a perfect storm of two very, very harsh conditions, the virus and leukemia, and it just, again, overwhelmed his body. So again, tough situation. But in the process of leukemia, right, leukemia will be associated with fever, weight loss, bone pain because of the bone marrow sort of issues. And because now there's too many white blood cells, it's sort of like the opposite of polycythemia. Right? Polycythemia, too many red blood cells clogs up the blood. Well, if we have leukemia, we have too many of these white blood cells, too many abnormal white blood cells that will start to diminish the hematocrit, so decrease the amount of red blood cells in circulation, diminish the platelet count, and that could be problematic as well. So not a nice condition for sure. So again, with that will conclude our discussion on the leukocytes. So again, to keep the PowerPoints and the files small, I'm going to stop this one here. I'll upload it, and then I'll get into the discussion on platelets and continue with this PowerPoint here. But good stopping point for white blood cells. So stop this.